In this lesson, we're going to be covering mixed effects models. As we go through this lesson, hopefully you start to notice that mixed effect models are just extensions of random effects and a little bit of fixed effects models combined together. We're going to start with introducing an example, the sunscreen example. There's no data right here. I'll show you it later on. So in our sunscreen example, a company wants to evaluate the effectiveness of two sunscreen products. A random sample of 40 subjects participated in the study. The company randomly selected 10 technicians from their worldwide staff to take the color reading of participants before and after applications of sunscreen. Each sunscreen technician combination or treatment combination was randomly assigned to 2 of the 40 subjects. Okay. So in this, the company wants to evaluate the effectiveness of 2 sunscreen products. So they only want to look at 2 sunscreen products. This statement right here is going to tell us we have a fixed effect because we only want to compare these 2 sunscreens. Okay. Then the next sentence that we want to pay attention to is the company randomly selected 10 technicians from their worldwide staff. This sentence right here is telling us they have a lot of people, but we're only going to be randomly selecting 10 of them. This is now going to be our random effect. So we have a treatment of sunscreen, which is fixed because we're only interested in 2. Then we have a treatment of technicians, which is going to be random because we're randomly selecting 10 out of all their staff. Okay. I want to note 2 other things. This sentence right here, random sample of 40 participants in the study. This is just a good way of creating your design of experiment as well. You're just going into the population and you're randomly selecting 40. This green line does not have to do with making our treatment a random effect. Also, each sunscreen treatment combination was randomly assigned to our subjects or our experimental units. This again, highlighted in green, is just good design of experiment protocol. Okay. So here we have a 2-way mixed model. It's mixed because we have one treatment as fixed and the other as random. So how we would do this is we would have factor A as fixed, and we would have A fixed levels, and then we would assign the other factor to have B randomly selected levels. It's arbitrary on whether factor A or B was random or fixed. In our notes, I'm just going to have A be our fixed variable and B be our random. Other than that, our total number of treatments is the same as we saw in our random effects model. Little n is our number of replicates, so our total number of EUs is capital N. As we move down to the statistical model, it should look familiar as any other 2-way factorial design we've seen. But now in this case, our mu is still our grand response, but our A is our fixed effect. So notice we don't have this kind of distributional assumption that we saw in lesson 9 with our random effects. Our beta is going to be our random effect. Okay, and we can notice that by having this distributional assumption. And then here's the thing to notice. We have AB. A is fixed and B is random. Whenever you have an interaction term where one of them is random, that interaction term will also be random. So in this case, our AB interaction is also a random interaction effect between the treatments and the technicians. And then we still have our random errors. And now, under this two-way mixed effects model, we only have 3 random, that's supposed to be variance. This is 3 variance components. Okay, component 1, 2, and 3. Notice we don't have a variance component for alpha because alpha is now a fixed effect. That's going to come into play when we look at our means and variance components. So now notice, if you're comparing to our random effect, our alpha I is now part of our expected mean. That should have a K. There should be a K there, but it's not important right now. Okay, so when you're fixed, it's going to start becoming a component of your mean, but our other 3 are going to be, and by other 3, I mean our beta j, our interaction term, and our epsilon are going to be derived through the variance. Notice that there's no longer a sigma squared alpha because alpha is being put into our expected means. Now, if we look at our ANOVA table, again, this whole part, the degrees of freedom, the sums of squares, or the mean squares, regardless of whether you're in a two-way factorial design with only fixed effects, only random, or a mixed, like we are right now, the degrees of freedom, the sums of squares, and the MS are all calculated the same as we saw in lesson 7 of the factorial design. Okay, what's different is your test statistics. So in lesson 7, when we only had fixed effects, the denominator was MSE, okay? In our last lesson, lesson 9, we saw that the denominator for our A and B, when both are random, is the MSAB. So MSAB would be underneath these. And then we saw that the denominator for this was MSE, okay? And again, those are all based on our expected mean squares. So for our mixed effects model, we're gonna follow the same kind of idea and look at our expected mean squares. This is a really good table. I really like this table because it tells us our expected mean squares under both are fixed, both are random, or now our mixed effects case. Again, for these notes, I'm assuming A is fixed and B is random. So let's think about this. If we were to test factor A, which is fixed, our hypotheses will be that alpha I equals 0 for all I, or our alternative, alpha I at least differs for one of them. Another way you could say that is there's no treatment effect or there is. And under the null, for our fixed hypothesis test, we would assume that the alphas are equal to 0. So if we scroll back up here, that means under the null, this goes to 0, and we'd be left with this term. This sigma squared of epsilon plus n times the sigma squared of our interaction. When we look down here, we notice that this now matches our expected mean squared for our interaction. So this tells us that for our F-test statistic, for our factor A when it's fixed, our F-test is going to be MSA over MSAB. Okay. Following the same thing, if we are looking at factor B, where factor B is random, under the null, we would assume that our sigma is 0. So that cuts this part out. And we can notice that these two are the same. And so our F-test statistic for our MSB is MSAB. Okay. Now, if we continue this thought process for our interaction right here, we just say under the null, our sigma squared is 0. That cancels out that. And then we can notice that again for our MS, if we were to do our F test for our interaction, it'd be MS AB over MSE. Hopefully, you guys are thinking, wow, this looks super similar, and it should. So in a two-way random effects model, in a two-way mixed effects model, your ANOVA is going to look the same. The caveat is the interpretation of our fixed effect, okay? So we'll get to that in a moment. Let's continue talking about another important part. So a follow-up analysis, when we were in lesson 9, a follow-up analysis was to look at the variance component estimates. And we can do the same thing here, but notice we only do it for our background noise, our interaction, and then B, which is our technician. Note, we do not do it. It's referring to the variance component estimate for fixed effect. Okay? And so in this case, if I was to ask you, oh, what's the variance component for sigma squared alpha or the fixed effects, you'd be like 0, because you don't do it. Or you don't do it. Okay, with that in play, let's go back to our sunscreen example, go over this, and then we'll generalize it to maybe a 3-way and talk a little bit more diverse. So again, we're here to evaluate the effectiveness of the 2 sunscreen products, which is our fixed effect. The company is going to randomly select 10 technicians from their worldwide staff. That is our random effect. And then we have just good design protocol. Here's the table for you. Yours is going to be colored. It accidentally printed out in black and white. Okay, this is the ANOVA table you'll get. I will show you how to do it in R and JUMP, don't worry. Note that our sunscreen technician interaction is random, so I'm going to put an R. Our technician is random, but our sunscreen is fixed, okay? So if we were to test the interaction, our hypotheses would be this. We would come here, we would look at the p-value right here, and we would make the conclusion that there's significant evidence to suggest that there is variability in the terms of interaction. Okay. Then we'd want to look at the main effect of B. In this case, B is our technician. We have our hypotheses, and then we're going to make our conclusion that there is variability. There's significant variability from technician to technician. Practically, what that tells us is that we might want to go and train our technicians on how to do these readings and whatnot so that there's less variability from technician to technician. And then our next thing we want to test is our main effect of A. Now notice that our hypotheses are the sunscreen has no effect versus the sunscreen has an effect. We look at our p-value. This is less than our significance of 0.05. We're going to reject the null, saying that there's a significant difference. Now note, from here at this point, with A being our fixed effect, we could go do a Tukey or a Fisher's analysis. But in this case, we only have 2 sunscreens, so it wouldn't make sense to do a Tukey's on only 2 sunscreens. But you can do it if you had more. That could be in a post-analysis for that. The post-analysis for our random effects is looking at the variance component estimation, where we have these formulas. very similar to what we've seen. You can also find the proportion by dividing the respective. These 3 question marks refer to whether you were going to use the interaction, beta, or epsilon. So you're going to take that, divide it by your overall. Okay. Now, I want to give you at least a more generalized look at mixed effects. In this case, we were only doing 2-way, where one is fixed and one is random, but in some designs, you might have more than just 2 I forgot my word. 2 effects, boom. So how to classify an interaction as random or fixed in a mixed effect. An interaction will be fixed if every factor involved is fixed, and an interaction term will be random if any factor involved is a random. So let's look at a 3-way mixed effect model to understand this a little bit better. So let's say we have 2 fixed effects. We have A and B that are fixed and 1 random, which is going to be B. This is going to tell us because A and C are both fixed, then this is going to imply that their interaction is fixed. The rest of the interactions, since the rest of the interactions include B, those are all going to be random. So here's a 3-way mixed effects model where A is fixed, B is random, and then our gamma is also fixed. So our AB is going to be random because it contains B and B is random. Our alpha gamma is going to be fixed because both components are fixed. Our beta gamma is going to be random because it contains beta, and our epsilon, i.e. our random errors, are also going to be random. This is definitely no longer 3 because we have 1, 2, 3, 4. So in this case, we would have 4 variance components. All right. Now, the protocol for testing general mixture effect models is if there's a significant fixed effect interaction, we want to explore. So this is very similar to what we would do with factorial designs that we learned in lesson 7. So similar to lesson 7. If we have a random effect interaction that's significant, we can proceed. This is similar to lesson 9. All right, so hopefully, I know this probably was a little bit faster than our other lessons, but hopefully you noticed that mixed effects models are just using a little bit of our random effects and using a little bit of our fixed effects models that we've seen previously. With that covers it. In the next 2 videos, I will be posting and talking about how to do this in software.